Alright, so now we're going to continue on the next problem for tutorial 6 of Control Theory class. And now we're going to discuss problem 2. So in this problem, we're given an open loop transfer function, g of s, and it consists of a pole, s plus a plus epsilon, over s plus a. And in this problem, we're trying to discuss what the effect of pole zero separation is to the transient and steady state response of a system given a step response. And in this case, the epsilon over here acts as the pole zero separation. And basically, epsilon can be any number. And then we're trying to see if epsilon goes closer and closer to 0, what happens to the step response. So the question can be broken down into two parts. The first part is find the step response of the system. And then the second part is how does epsilon affect the step response. So first of all, we have to find the solution of the step response for the system. And it is very important to note that in this problem, we have to find the step response of the system, which is step response of g of s given an input 1 over s. And this is different from step response of a unity feedback system, in which we have to find the closed loop transfer function and then give an input 1 over s to the closed loop transfer function. So here we have the output c of s equals to g of s multiplied by r of s. And then this is equal to the transfer function s plus a plus epsilon over s plus a multiplied by a step input 1 over s. So basically c of s is the step response of system, and this is different if the question is asking about the step response of a unity feedback system. So please read the question carefully. If I have to write it down here, we will have c of s over r of s equals to g of s over 1 plus g of s. And c of s corresponds to the step response of the unity feedback system. So these two are the different. So in here we basically just take the open loop and multiply it with the input, and here we have to first find the closed loop transfer function. So if we follow on over here, the step response of a system basically is in the time domain. So what we can do is, of course, perform an inverse Laplace transform of the system output, c of s. And then the question specifically mentions find the step response by taking the inverse Laplace transform of 1 over s plus a, and then use the superposition and differentiation rule to solve the problem. So if I have to rewrite c of s, I can break it down into two parts, s over s plus a plus epsilon over s plus a. And this is multiplied by 1 over s. So rewriting the whole term again, I'll write this term first. I'll have a plus epsilon multiplied by 1 over s plus a multiplied by 1 over s. And then the second term, I will have s over s plus a multiplied by 1 over s. So I will call this section over here C1 of t, and the second section over here C2 of t. Of course, the inverse Laplace transform will be C1 of t and C2 of t. So let's solve for the first part. Or I should call this C1 of s instead, and C2 of s. So if we solve the inverse Laplace transform, we can get C of t equals to a plus epsilon multiplied by C1 of t plus C2 of t. So that's the form that we want to find. So first of all, C1 of t equals to the inverse Laplace transform of C1 of s. And that is equal to, plug in C1 of s, we have 1 over s plus a multiplied by 1 over s. And to find the inverse Laplace transform of a function of this form by using the Laplace transform table, we can first express this equation as a partial fraction expansion. So we can have 1 over s plus a multiplied by 1 over s equals to capital A over s plus a plus capital B over s. And this is the partial fraction expansion. Solving the right and left hand side, we can have capital A multiplied by s over s plus a plus capital B multiplied by s plus small a divided by s. And then equating both the numerator of the left and the right hand side, we can get 1 equals to s multiplied by a plus b plus small a multiplied by b. And so a plus b equals to 0, and small a multiplied by b equals to 1. And we have b equals to 1 over a, and then a equals to minus 1 over small a. So our equation will become minus 1 over small a multiplied by s plus a plus 1 over as. And we can just take the inverse Laplace transform of these two fractions that are in their standard form, which is, let me rewrite everything again. So this is following from the step that we did up here. And the inverse Laplace transform of the first term over here is equals to minus 1 over a, which is the coefficient. And then inverse Laplace transform of 1 over s plus a equals to e to the minus at. And then for the second term, we have 1 over a, which is the coefficient. And then we have 1 for the inverse Laplace transform of 1 over s. So rewrite the equation, and we have 1 minus e to the minus at. So this is basically the first part of the step response that we have found. And if we go back to our equation of the output here, we can see that basically the second part is equal to the first part multiplied by s. So C2t t equals to C1t, C2s equals to C1s multiplied by s. And we know that multiplication with s in the Laplace domain corresponds to differentiation in the time domain. So what we can do now is C2 of t equals to d dt of C1 of t. So that is the step response equation for C2 of t, and we can get it just by differentiating C1 of t over here because of the rule of differentiation from the multiplication with s in the Laplace domain. So let me start with a new piece of paper. And what we have now is C2 of t equals to d dt of 1 over a multiplied by 1 minus e to the minus at. And differentiating this term, we have 1 over a multiplied by minus a e to the minus at. So we have e to the minus at. And with this, we can construct our general step response, which is equals to C of t equals to a plus epsilon multiplied by C1 plus C2. So we have C1 of t is equals to 1 over a multiplied by 1 minus e to the minus at plus e to the minus at. And simplifying, we will get a plus epsilon over a minus a plus epsilon over a e to the minus at plus e to the minus at. And further simplifying this term, we can get a plus epsilon over a, and then this term is basically 1, so we have e to the minus at minus and plus e to the minus at. So we are left with minus epsilon a over a multiplied by e to the minus at. And basically, this is our equation of the step response. And that is the answer for the first problem, first subproblem of problem 2. And next, now that we have found the step response, we have to find the effect of epsilon on the step response. And we know that the step response is equal to, let me rewrite everything over here, a plus epsilon over a minus epsilon over a e to the minus at. And we can find first the step response at t tends to 0, which is the initial component. And this is equals to a plus epsilon over a minus sub in t over here, sub in 0 as t, sub in t as 0, and we can get 1. So we have epsilon over a multiplied by 1, and this equals to 1. And then at t tends to infinity, which is the steady state, we will get similarly a plus epsilon over a, and then e over epsilon over a multiplied by e to the minus at, and t is equal to infinity, so we can get 0 over here. So our result is basically a plus epsilon over a. So As epsilon tends to 0, the initial step response is unaffected. But the steady state of the step response will tend to 1. So in other words, as the pole zero separation is very small, or as the pole is very close to 0 for this particular case of problem, the steady state error will tend to 0 as well. So basically, this is all about problem 2 of tutorial 6.